Alright guys, so this is going to be a recording for 12.3 Radians and Degrees, as you can see up here at the top. And I really don't like that feature. Okay. And I think this is a really easy lesson, so I'll go a little faster so that you guys don't spend too much time listening to me ramble on and stuff like that, so I'll kind of go kind of fast probably. Alright, so let's look over here, angles in standard form on the left, and what you see here is a y and x axis, and the axes are labeled in degrees, and it's like we're going around in a circle. So we start at 0 degrees, then as we go around the circle, we go 90 degrees, right? That's a right angle. We've gone 1/4 of the circle. And if we go another 1/4 of the circle, we're at 180 degrees, so it's halfway around the circle. And then 3/4 is 270 degrees, and that last bit puts us at 360 degrees. So what that means is that 0 degrees and 360 degrees put us both at the very same spot, right? This ray is 0 degrees and it's 360 degrees. And that ray on the x-axis is called the initial ray, I think. And the other ray that goes out like this, which is the other part of our angle, is called the terminal ray. It might be called terminal side. Pretty sure it's terminal ray, but we'll see if I'm wrong. And the most annoying thing about this is, in my mind, clockwise, this is clockwise going around like this. That's like positive, right? Because that's moving forward in time on a clock. But clockwise rotations in math are considered negative angle measurements for some bizarre, undesirable reason. And counterclockwise rotations, which are going the other way, right, going backwards around the clock in time, this is counterclockwise now, that's positive. Okay, so counterclockwise is a positive measure, clockwise results in a negative measure, and one full revolution, as we talked about, is 360 degrees. Okay? So from that, we want to sometimes draw out, we want to draw out our angles right here, just for some practice. So remember, this is 0, this is 90, and this problem says do 75. So one thing you should know is what's between 0 and 90, 45, right? So this right here at the halfway point is 45. So, if you were like drawing this on paper on an assignment, the only thing I'd really care about you doing with 75 degrees is that it's between 45 and 90. Like if you draw like down here and you call that 75 right there, or if you call this 75, that's not very good. But as long as you do something up here, and you call that 75, I'm happy with that. That's pretty 75-ish. It could be like 60, 75, or like they're pretty much the same number when you round down by 15. So no big deal. And we just went counterclockwise, right? That was counterclockwise 75 degrees, and that's why it's positive 75 degrees. Here at number 2, it's negative 160. Negative 160, remember this is 0 right here. So negative 160 is going around this way. And you know that this is 180, okay? And 180 and negative 180 are the same thing. Well, negative 160 is less than negative 180, so it's going to be like around, whoa, that's not even a straight line, right? It's going to be like right here. That's like negative 160-ish. 430 degrees is a little tricky, right? Like, where's 430 degrees on this? I said 0, 90, 180, 270, 360. Well, we can keep going, right? So this is 0, 90, 180, 270, 360, and then plus 90 again is 450. Okay, so if you put an angle, actually let me finish this first. So 430 degrees, and I should have, in these problems, I should have, done the initial angle too, and been more thorough on that. That's my bad. Technically, you need this other array also. Okay, so this is part of it being the angle. And 430 degrees, if 450 is up here, well, then 430 is going to be a little less, right? So like this is 430 degrees. And you might say, or 450 degrees, or 430 degrees. Yeah, 430 degrees. You might say looks kind of like 75 degrees, right? Like this angle and this angle look kind of the same. Well, as your degrees go up, you just keep going around the circle. And so if you were in a situation where, for example, if I told you, if I drew this angle, right here, and I said, how many degrees is that to you? Technically, you don't know. Technically, it's 90 degrees, but it's also 450 degrees. And it's also, what 360 times 2 is 720, plus 90 is 810, so it's also 810 degrees, and so on and so forth like that. And also, it's also technically negative 270 degrees, right? If I went around this way, if I went around clockwise and went negative, that's negative 270 degrees going around this way. So when I give this to you and say, how many degrees is that? It's technically all these answers. They're all technically correct, okay? In general, though, we default to positive and the smallest number possible. So on a test, you might be asked, what is this angle? And in that case, you should just say 90, if it were like fill in the blank. But one kind of question you're definitely going to have on your test over this content is, we'll draw an angle like this, and we'll give you a list of angles. And we might say, select all of the options that could represent this image. And so, if you had a big list of numbers, you'd want to check these 4 off. For example, you'd want to cover all your bases. They're all correct answers. This line represents all of these numbers, okay? So that takes care of that. Okay. Let's talk about radians. So radians will seem confusing to you at first, but they're just another unit of measurement. So think to like inches and feet, okay? If you have 12 inches, that's the same thing as 1 foot, right? And if I tell you, give you the number in inches or give me the number in feet, that's really not anything to be intimidated by, right? You divide by 12 or multiply by 12. And radians are the exact same idea. Radians replace degrees as another measurement, okay? And I'm gonna go slightly up here. And just to have something to draw on with that, so now my circle doesn't make any sense. If we're going around, this is still 0, okay? And once I go halfway around, that's pi. And going all the way around is 2 pi, okay? So that means that 180 degrees is the same thing as pi, and 360 degrees is the same thing as 2 pi, and that also means that 90 degrees is the same thing as pi over 2, and 270 degrees is the same thing as 3 pi over 2, okay? So if you'll get questions on your test where you have to tell me what 90 degrees is in radians. You need to convert that. So we're going to talk about that next. And it's really not hard, okay? You just have to think back to, I know in science you've done this stuff, right? If you have 3 feet, and I say convert that to inches, you learned about something in chemistry called dimensional analysis, which is just a fancy way of saying we're going to convert units. So 3 feet, and then what's my ratio? My ratio is 1 foot to 12 inches. So I put my 1 foot on the bottom and my 12 inches on top. And what happens here is my feet cancel, and I now do 3 times 12, which is 36 inches. So 3 feet is the same thing as 36 inches, and I just had to use my ratio of inches to feet to convert those units. And radians and degrees are the same thing. We just said that 180 degrees is the same thing as pi. So that means we're going to use this ratio of 180 degrees over pi to convert from radians to degrees. Or if we want to go from degrees to radians, we use pi over 180, okay? And the key thing to remember here is whatever you're trying to get rid of, you put on the bottom, right? If you look at my feet and inches example right here, one sec. Yeah. Ooh, okay. If you look at my feet and inches example right here, I was trying to get rid of feet and go to inches, right? So I put feet on the bottom. Why? Because I want to cancel my units. And you cancel these units by dividing. If I put feet on top, if I flipped these, I would get 36 feet squared over inches. And like, if I move the 12 down too, then it would be 1/4 feet squared over inches. And like, what does it even mean? Feet squared over inches. It means something, but we're not going to talk about it. Anyway, so that's the basic idea behind what we're doing here. And next week, and we'll talk more about how, not next week, but the week after that, we'll talk more about how you can do trigonometry. Actually, I don't have to erase these anyway. With things above 360 degrees. Like I can give you something like 44 pi over 3, and you should be able to tell me how many degrees that is. Things like that. I lost track of myself. Okay, here we go. So I think this is a good perspective. So I'm just going to do one of each of these and move forward to try and keep time down, because I noticed the lectures have been going a little long. I don't want them to be too long for you guys. So 30 degrees. So I start with 30 degrees, and I want to get rid of degrees, right? So I multiply, and I put my degrees in the bottom, 180 degrees, and on the top I put pi. Okay? And the thing is here, what you don't want to do is, let's see, 30 pi over 180. Here we go. What you don't want to do is type it in a calculator and do this. Okay, this is big bad. You should not tell me that it's 0.52 radians. That's not wrong, but the goal is for you to be able to give an answer that involves pi. Typically, with radians, you want to have pi in your answer, and the angle measurement being written in terms of pi is a good indicator of it being in radians. Technically, you could do degrees and have a pi value in there, but it's just kind of a scumbag thing to do. You don't want to do that. And if you see a number without pi, that's typically a good indication that it's in degrees. There's no like perfect way to know, but because people often just leave the degree symbol off, and in radians you don't write the degree symbol anyway, so it can get confusing. But typically, if there's a pi in there, that's radians. If there's no pi, then it's degrees. I like pi, but I don't like radians, so that doesn't go well together. So what do we do right here? Well, let's go back to our problem. We want to reduce this fraction, right? So I have, I'll just write it over here, 30 pi over 180. And the first thing that should be obvious to you is that we have zeros here. So let's cancel those zeros. So now I have 3 over 18. What's 3 over 18 reduced to? Well, 3 over 18 reduces to 1 over 6. So this is now 1 pi over 6, and 1 times pi is pi, so it's just pi over 6. Okay, and this is our final answer. This is converted to radians. So that's all you have to do. You just take whatever starting number you have, multiply by pi over 180, reduce the fraction, and you're done. Okay? In fact, I'll do one more. Let's see. So I have 150 times pi over 180. Okay, so let's just skip the step and cancel out our zeros. So I have 15 pi over 18. 15 pi over 18. And I can divide both of these by 3, right? 15 divided by 3 is 5. Let's put a little line here. 15 divided by 3 is 5. 18 divided by 3 is 6. So the answer is 5 pi over 6. And that's our answer. Very easy. The negative doesn't affect anything, so when you try this problem out, don't be tripped out by it. It just becomes negative whatever it would normally be. And your answers can be, you can have a higher numerator than a denominator. It's not a big deal. So I'll leave that one for you guys. And this problem, same idea. We start with 4 pi over 3, and we multiply it by, instead of doing pi over 180, right, I want to get rid of my pi, preferably by eating it. Especially if it's rhubarb pie. Rhubarb pie, by the way, very underrated pie. People are all about like apple pie and blueberry pie and pumpkin pie, and those are all fine pies, don't get me wrong. But rhubarb pie, if you haven't had rhubarb pie, I really recommend trying it. It's just a highly underrated pie. I don't even know what rhubarb is. I've never seen a rhubarb in my life, except for when it's cooked in a pie. It's pretty good. Okay. So instead of doing pi over 180, we do 180 over pi. And the first thing that should be obvious is that we cancel our pi's right here. Okay? And my preference usually is to divide and then multiply. If I can divide things to simplify my multiplication, I will do that. So I do 180 divided by 3, and what's that? Well, 18 divided by 3 is 6, so this is 60. Then I do 60 times 4, and 60 times 4 is 240. So this is 240 degrees. And we're done. That's it. Okay. I'll do one more. Just, I'm in that good of a mood. I think this is a negative sign right here. Let me darken it in to make it more obvious to myself. Well, it looks really good, just like it's printed there. Okay. Times, and it's the same thing every time. 180 over pi. And for those of you who feel like this is familiar, yes, you did learn this in geometry. But we're doing it again because, I don't know, why not? That's what we do. Pi, these cancel. And because, you're going to do this a lot. How do we reduce this? 180 over 36. Well, forget about the 0. What's 18 over 36? 18 over 36 is the same thing as 1/2, right? So this is the same thing as 10 over 2, right? I'm doing that right? 10 over 2? Yeah, this is 1/2, and this is a 0, so it's 10 over 2. And then 10 divided by 2 is 5, so this is just 5 times 5, or negative 25 degrees. And that makes sense because negative 5 pi over 36 that's a pretty small fraction, right? So we'd expect a small degree. That makes sense with our values. Okay. Moving on, moving forward. We're already half done, making good time. Trying to keep the time down for you guys. Coterminal angles. So coterminal angles are also really easy. It's just going back to the idea before where I said, hey, if you have an angle like this one, let's just put an angle like this. That's right, I could just make it thicker right here and do that, huh? That's just, no, not that thick. That's good. Okay. If I have an angle right here and I told you guys, hey, this is 90 degrees, But you could also add 360 degrees to that and make it a full revolution, and now it's 450 degrees. And I could add another 360 and blah, 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 and so on and so forth. And I also said, hey, it's also negative 270 degrees, okay? So that's all these problems are asking for, okay? So it says, give two coterminal angles. Coterminal just means it's the same angle, but after one revolution around the circle, negative or positive, and it says give one positive and one negative. So all I have to do here is do 65 plus 360 and 65 minus 360. That's it. That's all we're doing. So we do this math. 36 plus 6 is 42, right? Plus 5. So I have 425 degrees. And then minus, that's going to be negative 295 degrees. So that's it. We're done. Those are our coterminal angles. And now for number 12, I'm not going to do number 11 because this is easy, right? You use the same thing, plus 360 minus 360, you're done. 12 and 13, though, these are written in radians. So remember I said a full revolution going around a circle is 2 pi. So for these ones, we do 13 pi over 18 plus 2 pi and 13 pi over 18 minus 2 pi. Okay, so it's like, I guess a little harder because you have to deal with fractions, but it's not too bad because what's 13 pi over 18? Well, we want to take this 2 pi and know that 2 pi is the same thing as 36 pi over 18, right? Give it the same denominator as this over here so we can add them. And 36 plus 13 is 49, so this is 49 pi over 18. Yes, let's just redo that. 18. Okay. And 13 pi over 18 minus 2 pi. Doing this kind of subtraction, the smart thing to do is to flip the numbers. So do 2 minus 13 over 18. And if you do that, you get 1. Hold on, let's rewrite this 2 as 36 over 18. Okay, so remember 2 pi is the same thing as 36 pi over 18. So let's do 36 over 18. Okay, 36 minus 13 is 23. So it's 23 over 18, but I flipped the numbers. And you guys might know this, but if you flip numbers, you can, let me say this, if you're going to subtract two numbers, you can get the same answer of this as if you flip the numbers, but also flip the sign. So this is 23 over 18. And, technically there's a pi there, but I didn't include it. So which means over here, this is negative 23 over 18 pi. Okay? So that's a handy trick, because doing this subtraction can be tricky. Flipping the subtraction and then flipping the sign is going to save you a lot of heartache, a lot of headache, a lot of ache. Oops, I gotta delete this stuff. Reference angles are very simple, and I don't even know what I know what you use them for. That's because we're gonna use them in 2 weeks, I guess, I think. But I don't use them much in daily life. Okay, so 225 degrees. First thing to note is that it's positive. Positive means that you are counterclockwise, right? So, positive means you are clockwise. Positive clockwise. Wait, I'm tired. clockwise is negative, counterclockwise is positive. So we're going this way, counterclockwise, and this is 180, which means 225 is a little past this, right? So like this is where our angle is on this problem. And the reference angle is just asking us, hey, look at the angle you made, this angle right here, which is, I'll do it a different color. This angle right here, look at this angle right here. And how many degrees away from the x-axis is that? So how many degrees are these two things apart? And that's not really hard because you know that going halfway around the circle is 180 degrees. So what's really asking is how far past the halfway point is this, which is just 225 minus 180, which is 45 degrees. So that's our reference angle. And you'll understand why we care about this reference angle more when we talk about the unit circle in 2 weeks, okay? I'm not going to worry about it right now. So I'll let you rock 15 and 16. Let's knock this last 2 sections out. Or maybe I'll just do this one, and I think I'll do the top one maybe and let you guys do the bottom. Let's see how hard it feels. So it's just talking about using trig functions for the Pythagorean theorem, and we've already gone over that, right? The only thing only to think about is points in space. So if you're given a point x, y, well, the x value is the same thing as the x component of the triangle, and the y value is the same thing as the y component of the triangle. So for example, number 17 says you have a point at 5, -2. Well, let's do some hash marks. So here's 5, -2 right here. So what that means is that because this is 5, -2, we can make a triangle like this. And what are the components? This has a height of 2 and a length of 5, which means you can Pythagorean theorem for this right here, right? That's 25, 29 squared root of 29. And now you have this triangle. Now you can do SOHCAHTOA stuff with it, okay? So if I do that over here, here's my my Pythagorean theorem formula is just going to be y squared plus x squared equals r squared, okay? And sine, you know, is, if this is my theta right here, what's going to be sine? That's so, right? Let's write out SOHCAHTOA again for your memories. And so sine is opposite over hypotenuse. So here's my opposite y over hypotenuse r. So it's just y over r. And remember, cosecant is just the inverse of this. So it's r over y. Don't even think about it. Just flip it. Cosine is adjacent over hypotenuse. So my adjacent is x and my hypotenuse is r. So it's x over r. And again, secant is the reciprocal of cosine. So this is just r over x. Tangent is opposite over adjacent. So my opposite is y, adjacent is x. So this is y over x. And cotangent is the reciprocal of tangent. So it's x over y. That's all you have to do. So on this down here, that was something randomly falling in my house. I have no idea what it was. Probably nothing to be worried about. I have to erase these things, I guess, to go through these last problems. So on this problem right here, I said this is 2, right? This is, whoops, let's drag her. This is 5, and this is root 29. So if this is my angle right here, you don't take the, you take the angle that's coming from the origin. Don't take the angle out here. So this is theta, which means this is the, this out here is the opposite, this here is the hypotenuse, and this here is the adjacent. So if I'm using SOHCAHTOA, sine of theta opposite over hypotenuse is O over H, so it's 2 over root 29, which when we multiply the numerator and denominator by root 29, this becomes 2 root 29 over 29. Cosecant, the inverse, stick with this one and flip it, right? Because if you flip this second one, then we have root 29 on the bottom again, which means we have to simplify it again. It's a mess. Flip the first one, and it's just root 29 over 2. That's easy, right? Cosine, adjacent over hypotenuse. Adjacent is 5, hypotenuse is 29, so it's 5 over root 29. And then, of course, we have to simplify, so it becomes 5 root 29 over 29. And then for secant, flip this one, so it's root 29 over 5. For tangent, that's opposite over adjacent, so O over A is just 2/5, and the cotangent's the reciprocal of that, so it's 5/2. Look at that, you guys tricked me into doing the whole notes for you. Tricky kids. So yeah, I think that's a pretty simple lesson, I think, if you've understood the previous ones. The only other thing I wanted to talk about with you guys is I did promise you all that I had a friend, I said, and you'll just have to trust me on that I have friends. And I said I would give you a word problem that illustrates how, can't I make this bigger? Why are you, okay, that's weird. I said I'd give you a word problem that demonstrates, that's just weird how it gets bigger. It gets bigger at the one at work. But anyway, I said I would demonstrate to you guys how trigonometry is used by my friend in game development. Okay, so he created this word problem for me, and it's not, it doesn't have an answer. It's a conceptual problem to make you think about exactly what's being done in game development. If you don't care about this, you're welcome to close the lecture. I'm done with the actual content portion. I just wanted to give you this example. So let's say you have a character in a video game, and it's a first-person video game. You know, my friend works for Bethesda, so he works on things like Doom and Elder Scrolls and Fallout, which are all first-person games, right? So the way the game works is you have a character here, and the game is first-person, and you have something called a field of view. And your field of view looks like this. This is like the stuff that's visible to you, and out back here is, below that dot, is the world that you can't see, right? It's behind your character. And let's say that we have a tree right here. Okay, so this is my tree. And the question, and this field of view is 90 degrees. It's a right angle, let's say. That's what he told me. So I'm going to go with that. It's a right angle. And there's a distance between you and the tree, right? Like we can draw a line out here, and we can make a triangle from this to figure out how many degrees that you are from this tree. And because this whole field is 90 degrees, you know that each half of this is 45 degrees. Okay, so what they do is there's a map that the character is in within the game, and that has coordinates. You know, let's just say you're like at 427 or something like that, and up here this object is at let's say it's at 1432 or something like that. Well, you can use those coordinates to find out this measurement right here, and you can also find the coordinates of the x and y components. And using those components, you can figure out the number of degrees that are between the character and the object, okay? Now, let's imagine that this character moves forward a bit. So I'm going to redraw this, hopefully not poorly. Oh, I already failed. Okay, that's not too bad. And this character, so the character was here, but the character moved forward and is right here now. So this is their new field of view, okay? And the question that he has to calculate in the game is this tree still in here? Or is the tree outside of the field of vision, or is it inside the field of vision? And he has to program the game to make triangles and use those triangles to calculate the degrees. And if the difference in degrees between the person and the tree is more than 45 degrees, that's actually how the game knows that there's no tree to be in your view. Those of you who have never done any programming might be asking something like, well, can't the camera just see if the tree is there? And the answer is no. The camera doesn't have like eyes like you and I think of it. Rather, the game has to be programmed to move the objects as you move the character. So the game only knows that the tree is no longer in vision once they've done this calculation. Furthermore, this is used a lot in things like spawning and despawning for graphics. If you've played any Bethesda games or any games that have a wide field of view, you know that you can only see so far ahead of you, right? As you move forward, graphics for things like trees, mountains, and characters start to generate, okay? And the thing is that takes processing on your game system. And the game system or computer can only handle so much processing at once. So you need to think about at what point do we start at what point do we tell the computer to start generating those graphics, right? And that's trigonometry too. You have to figure out how close they are based on the degrees of difference. And similarly, why do we care about something being outside the field of view? Well, once something is outside of the field of view, you don't have to keep track of that graphic anymore. And believe it or not, like imagine you have a character who's running around chasing you. You know, you're running away from something in combat. You stumble across something that's too strong for you, and you decide to run away so your character doesn't lose all his or her life, or its life. You know, if you're playing a non human character. Well, if the character that's chasing you is no longer in your field of view, it's efficient for the game to stop generating its graphic, because regardless of whether or not you are looking at the object in the game still has to generate its graphics and keep track of their animations, even when you're not looking at them. And so game designers have to manually program the game to say, hey, this object is no longer being looked at, so we can stop updating its graphics. We can stop doing animations for it. And that frees up memory for the game to do graphics for other things that you're actually looking at. If you never actually freed up that memory by doing the trigonometry, well, then eventually the game would be keeping track of everything that you've ever seen. And actually, funny enough, Morrowind, which was Elder Scrolls 3, had an issue like this, where it did not despawn something in the game very well. I'm not sure what it was. But the longer you played, the slower and worse the game got, to the point where it was unplayable. You know, I had over 100 hours in this game when I was in high school. And, you know, I had to stop playing, because after 100 hours or so, the game was a slideshow. you couldn't see animations. Things just teleported around because the game couldn't handle generating the graphics for new things very well because there were so many old things that it was still dealing with. So that was unfortunate times. Okay, so I hope that gave you a good example of how trigonometry gets used in something in the real world, so you don't think this is a total waste of your time. Okay, all right, guys. Hey, kept it at 40 minutes. That's not too bad, right? Yeah, maybe it's still terrible. Who knows? Have a good night, guys. Bye.